I'm not actually going to present any experimental results on the topic of the conference, so I just want to clear that up before anybody is disappointed. Really, my talk is going to be, to some extent, an announcement or an advertisement, if you like, for this new Waterloo-ALLS facility. And what I will do is I'll talk about that at the beginning of the talk, and then I will talk about some of my kind of personal motivations for getting this new facility working and running, which don't really have any bearing on quantum interference. So apologies for that. So there's lots of people just want to thank for being involved in the work that I'm going to show here. So I'm going to show some oldish results, which I think are still quite important. Okay, so before I start, though, I just want to give you a couple of pieces of information, because I think it's always important to tell people where is the University of Waterloo. This is a map of North America, and Waterloo is where the end of that little arrow is there. It's slightly over to the west of Toronto, and the other lab that I'm talking about here is the Advanced Laser Light Source, or ALLS, which is in Varennes, which is just outside of Montreal. Another important thing to do before I start really is to just acknowledge the fact that the University of Waterloo is situated on First Nations land, and in particular the Anishinaabe group. And so it's a very important thing in Canada that we recognize these areas, these rights. Okay, so here's the punchline really of the talk. It's probably going to be quite a short talk. In 2017, the Canadian Fund for Innovation approved a $12 million upgrade to the Advanced Laser Light Source in Montreal, a facility headed by François Legaré. And this application included institutions in Canada such as NRC, University of Ottawa, and University of Waterloo. And an important part of that application from University of Waterloo's point of view was this Waterloo-ALLS reaction microscope, which is a kind of facility within the facility, which is jointly managed by Waterloo and ALLS. And this was funded in 2017, and the timetable for it becoming available to users was something like 2020 to 2021. So obviously we're looking at 2021 now. And this is a typical commercial reaction microscope system produced by this company, Runtech. And the one of the important aspects of it is that it includes two detectors which have low dead time. So it means that you can hopefully detect more ions and electrons in coincidence. So this is a fairly standard piece of experimental equipment these days, and really it relies on the fact that the laser systems themselves are going to be upgraded. And so one of the new laser systems, I'm not going to go into too much details about these, but one of them is a fiber system, and we've had discussions about these new high repetition rate, high power fiber lasers before in the conference. So this system is nominally 2 millijoules at 100 kilohertz, and the ALLS team have pioneered the technique of stretching using a stretched hollow core fiber to generate either few cycle pulses or shorter pulses. This is a little bit of a paper from a couple of years ago, 2018, where they're taking creating a few cycle pulses with 6 meter long fiber. So that's just the pump, and that then pumps another couple of laser systems, OPCPA and AO PDF systems, giving and again these are kind of estimates of the current best estimates, but there will be a attosecond beamline as well as this, all of which are going to be running at very high repetition rates. And this is the really the important aspect, along with the new wavelengths that are available. So if, as I say, this is actually a user facility, and so if anybody is interested to maybe use this facility to look at some of these interesting quantum interference effects, etc., then please do contact me, and we can discuss how that could happen. There are other experimental end stations, of course, in the facility, and Haida is the person to contact there directly at ALLS. Okay, so that's my little ad for this new facility. And I just talk a little bit about my motivation for this, because back in 2014 we were doing experiments on proton migration imaging in the acetylene molecule. So this is my background. It's really imaging of the nuclei rather than the electrons in the system. So here we look at this acetylene molecule, specifically ionized to the first ionization stage, and that's quite an important aspect. I'll come back to that in a second. Basically, the proton from one end of the molecule makes its way to the other end and becomes a stable molecule known as vanillidine. And it's a really nice example of this process, which is fundamental for so many different chemical reactions and life itself. Just to give it a good background. So what we did in the experiment is we used a 266 nanometer pump laser, which is kind of third harmonic from the 800, to excite and ionize specifically into this first excited state of the singly ionized molecule. This is important because if you just go to the ground state of the 1+ molecule, it doesn't undergo proton migration. So then after that, you can watch this wave packet moving and the molecule changing from the linear to it's first an intermediate state before it reaches vanillidine and crosses the conical intersection. So this represents here the probe pulse, at different times. So this is the scheme here. So you come along first with the 266 onto the acetylene, and second with the probe pulse 800 onto the moving molecule. And then finally, we observe a triply ionized molecule, which is broken up into 3 fragments. So this is where the ion side of the reaction microscope comes from. This is what we were using at the time. And in order to actually kind of quantify how much of this proton migration is taking place, then we basically look at everything in the frame of the CH plus. So we create a CH plus, a C plus, and an H plus, and measure the momentum of the H plus relative to the CH plus, which is always along the x-axis. The red here means there's a lot of signal. So as you'd expect, the molecule starts off straight. After some time, blue here means that we've lost signal in the linear molecule, and it's got this more bent structure. And then still further on, the vanillidine is more formed fully. And then just by dividing those Newton plots in half, we can say where the acetylene turns into the vanillidine, and measured the time scale of that. So this is a nice experiment, and it was published in Nature Communications. We even made a movie of it and compared it with a horse. But the statistics were not as good as we would like them to be. This was done with a 5 kilohertz laser system and a basic delay line detector with significant dead time. We would like to repeat this and also keep the information there from the electrons as well. And so now where are we now, or soon, or next year, or sometime in the future? Nobody really knows, thanks to the pandemic. But we're looking at a 100 kilohertz system with minimal detector dead time. So this is going to be useful for not just for this kind of work, but also for these nice quantum interference type experiments. Okay, so that's a rather short summary of what we've been doing, and hopefully it's something which people will be interested in. And yeah, thank you very much. And for my next talk, you can ask me about what it's like to try and survive the Nobel Prize for your lab colleague. Thanks very much.
Thank you very much, Joe. Thank you very much for the talk. So we have plenty of time for questions and answers. I remind you that we can get your answers from the Zoom channel and also from the Slack channel. So maybe I can start and just asking a very simple question. Well,
yeah.
This new system, 2 things. One is that do you expect a 20-fold increase in the number of counts that you will get because you went from 5 kilohertz to 100 kilohertz? And the other one is related to the previous talk, that when you go to these mid-IR wavelengths, then the particles become much more faster. And if you want to see this interference effect or slight features on this, then you will need probably 2 challenging things. You will need high resolution and also so very large limits. I mean, you will have to accept very large velocities of the electrons. So this system, what did the system could cope with this? Okay,
that's a good question. So at the moment, the configuration of the system is open to negotiation and discussion with people. So this is one of the reasons I wanted to talk about it at this conference. Yeah, because it's one thing to set it up for one kind of experiment, and then that might not optimize it for another. I mean, it's reconfigurable to some extent, but we're not experts in this particular piece of kit. So I'm sure that we're gonna find the issues with trying to do that kind of thing. But maybe we can find a kind of a happy medium which allows us to cover a range of different experiments. As far as the factor of 20 count rate, I'm certainly hoping that something like that is achievable. We'll have to wait and see how that turns out. In the past, we've kind of developed algorithms to try to help us to push the count rate as high as we can without having issues of too many ions. So hopefully the new hexagonal detection system will help us to detect more of the fragments from the ions, which is what you need for a coincidence to be working well.
Okay, so maybe while we wait for some other questions, maybe it's also a related question on the amount of data that you will have to collect, because now if you increase the repetition rate that much, and normally Coltreams stores already big chunks of data, and then you will have more channels too. Would you need a very sophisticated infrastructure to deal with that?
Yeah, that's a great question. That's one of the issues that we're struggling with at the moment. As I showed you on the map, Waterloo and Montreal, and it's not like I can drive there in the morning and pick up a hard drive and take it back to Waterloo. So we'll need to have quite a bit of kind of onboard memory and storage there in ALLS. But we kind of envisaged doing some kind of cloud analysis. So we'll see how that turns out. But there's definitely opportunities for developing quite substantial data handling systems, actually. So we're trying to work with Google. We have a Google in Waterloo, and maybe they're interested in helping that. It's maybe not the kind of data that they're interested in, but you never know.